Welcome viewers to the third segment of the fourth lecture for the online series of lectures for the course of Dynamical Systems. So towards the end of the last segment, we proved an important result which was stated in terms of proposition 1. Now, in this last segment of the fourth lecture, we'll focus on a few examples and work out the corresponding limit sets. Let us study a case first where the omega limit set of an orbit turns out to be empty. So we'll study a case where omega limit set of an orbit turns out to be empty. Okay, let's refer back to the example of example 5 of lecture 3. Example 5 of lecture 3, where the flow map theta from R cross R2 to R2 reads, the flow map reads theta t comma pq is a vector in R2 is equal to e to the lambda t 1 t 0 1 pq. And this is going to happen for all t in the set of real numbers, and this pq vector is in R2. This is our equation number 11. Okay, so we're going to study this dynamical system where we want lambda to be strictly positive, and let us focus on the orbit of 1 0, of the point 1 0, of the vector 1 0. Okay, so points or vectors belonging to the orbit of 1 0 are of the following form, So just take P and Q to be 1 and 0 respectively. Okay, and we immediately see that if we choose P to be 1 and Q to be 0, then this is going to take us to, this is going to give us e to the lambda t times 1 and 0, right? So which we can write as e to the lambda t 1 0, right, for all t in the set of real numbers. Okay, so let me erase this part. So this is what we get. So the points in the orbits are of this form. We immediately see that the norm of this generic vector in the orbit it is nothing but just e to the lambda t, right? And this is, so since lambda is taken to be positive, this goes to infinity as t grows big enough, right? As t approaches infinity, this guy, the norm of this vector, grows without any bound, since lambda is positive. We therefore have the omega limit set of the orbit of the vector 1, 0 is empty. Okay, there is no point. There is no element in this set. Okay, so this is an example where we can see that the omega limit set can be empty. A limit set can be empty. We need some more definitions to, to have more restrictive situations than orbits. Let me give those definitions now. Some more definitions. Definition: semi-orbits. Let theta from R cross U to U denote a dynamical system on an open set U of R to the n, R to the n, given P in this open set U, the forward semi-orbit of the flow theta through P is the set gamma P plus defined by gamma P plus is equal to the points of U such that the point can be written down as theta t comma p for some t greater than or equal to 0. Here's the thing, we just take positive or 0 t's only. Okay. Similarly, the backward semi-orbit through P denoted by gamma P minus is the following set. Gamma P minus is going to be the collection of all the points in the open set U such that x can be written down as theta t comma p for some negativity. Okay, observe that here gamma p, the orbit of p, is the forward semi-orbit union, the backward semi-orbit union the forward semi-orbit. Okay. Again, the example 5 of lecture 3 being revisited here. So example 5 of lecture 3 revisited. So we have written down the flow map in equation number 11. Let theta r cross r2 to r2 is as given in equation 11. And what was equation 11? Let me write it for you again. Theta t comma pq is taken to be e to the lambda t 1 t 0 1 pq for all t p q in R. So that was equation number 11. So let us consider the dynamical system given by this flow map with positive lambda. Then one immediately finds out that the forward semi-orbit of the vector 1 0 is given by the collection of vectors in R2 such that the x component is greater than or equal to 1 and the y component is just 0. Okay, well, why this is the case? This is very simple, since e to the lambda t. So remember that the vectors were for the orbits were given by this, right? E to the lambda t and 0. And this is the case since e to the power lambda t is greater than or equal to 1, as we are just taking, according to the definition of forward semi-orbit, just the t's for which t is greater than or equal to 0. Follows from the graph of the exponential function actually, which is e to the lambda t, and this is 1, right? And since we are only considering this t's only, the positive or 0 t's, so we are just taking everything above 1, right? So that's why. So this is an infinite strip, unbounded above, because we take, so y is taken to be 0. Y is equal to 0 and x is greater than 1, means that you take everything to the right, right? This guy, it's unbound and hence non-compact, right? Okay, so this is the forward semi-orbit corresponding to this vector 1, 0. And see that the backward semi-orbit for the vector 1, 0 is given by all those vectors in R2 such that the x component lies between 0 and 1, because we are just taking all the negativities now, and for which e to the power lambda t can be anything between 0 and 1. So we take all the vectors of R2 for which the x component lies between 0 and 1, and y component is identically 0 because the y component is 0 on here. Okay, so here in this picture, we try to draw the backward semi-orbit, and that is going to be this point from 0 to 1, right, along the x-axis. Okay, so for the forward semi-orbit, everything is greater than 1 and y is equal to 0, so meaning that if this is 1, everything greater than 1. And for backward semi-orbit, we are going to have everything between 0 and 1. This is a compact set, as we can see, because we can find always a sphere or a ball of radius r that is going to contain everything here. So it's bounded. It's bounded, but for this case it's unbounded, and for this case it's going to be bounded, right? The backward semi-orbit is bounded, while the forward semi-orbit is going to be unbounded. Now, in the following proposition, we'll see that if the forward semi-orbit is bounded, then the omega limit set of the corresponding orbit is non-empty. Similarly, if the backward semi-orbit is bounded, then the alpha limit set of the corresponding orbit is non-empty. Okay, let's see. So let me write it down here. So we are going to see now here that in the following proposition, we'll see that if the forward semi-orbit through P, semi-orbit of the flow theta through P is bounded, then the omega limit set of the corresponding orbit is non-empty. Okay. Similarly, if the backward semi-orbit of the flow theta through the point P is bounded, then the alpha limit set of the corresponding orbit is non-empty. This is what we are going to see from the following proposition. So in the previous example, the example 5 of lecture 3, in the previous example, note that the backward semi-orbit through 1, 0 was bounded, right? Remember that if this is the xy plane, this is the x-axis, this is the y-axis, and so this is 0 and this is 1, this is 2, and goes onward like that. So the backward semi-orbit for the flow theta through the point P is 1, 0 was given by this strip, right? This finite strip, and this was bounded, as we have seen earlier for the previous example. And we have earlier seen that the alpha limit set of this point of the orbit of 1, 0 is precisely the 0 vector, right? So indeed, we see that the alpha limit set of this orbit of 1, 0 vector is indeed non-empty, right? It's a consequence of the fact that the backward semi-orbit through the point 1, 0 is bounded. Okay, good. So let me state the proposition 2 without any proof. Okay, let me state proposition 2. Let theta from R cross U to U be a dynamical system on the open set U an open subset of R to the n, and P is a point in this open subset, right? If the forward semi-orbit for the flow theta through P lies in a compact subset of U, then the omega limit set of the orbit of P is non-empty compact and connected. Three important features. It has to be non-empty, it is compact, and it is connected. So two topological properties, very important. The omega limit set is non-empty, compact, and connected. Similarly, if the backward semi-orbit for the flow theta through the point P lies in a compact subset of U, then the alpha limit set of the corresponding orbit is non-empty compact and connected as before. Compact and connected. The proof is omitted, okay? So the proof can be found in the references I mentioned in the first lecture. So the interested readers are advised to go over the references for the proof. Okay, so a few more examples to end this segment. Let me go over to example 2. Of lecture 3. Where the flow map theta from R cross R2 to R2 was given by theta t comma PQ is equal to its rotation by angle t, cosine t minus sine t, sine t, cosine t, PQ for all t, p and q in R. Okay, so this is the flow map of the underlying dynamical system. So we have seen in lecture 3 that the flow above this one obeys the following system of differential equations. System of differential equations can be verified by calculating the infinitesimal generator of the underlying dynamical system. So dx over dt is equal to minus y, and dy over dt is equal to x. Okay, so this we number by 12. So its orbits consist of the singleton, 0, 0, okay, and concentric circles, around the region. So like this, okay. So this is a singleton, this is the region 0, 0, and there are other orbits which are concentric circles about this region. Okay, these are all orbits for this dynamical system. Okay, for instance, we can take the point 1, 0 and take its orbit. Okay, we will see that it consists of all the points xy in R2 such that they lie on the circle of radius 1 centered at 0, 0. Okay. So now our duty is to show that the omega limit set of this orbit is the orbit itself. This is what we want to show now. This is equation number 13. Okay, let me erase. Let xy be a point in this orbit of the vector 1, 0. Okay. Then by definition of an orbit, there exists t0 in this interval, finite interval from 0 to 2 pi. So because in this example, the example that we are studying, t is an angle, and angle can be from 0 to 2 pi. Okay, so there exists a point and there exists an angle such that x comma y is going to be theta t0 1 comma 0. 1 comma 0 since we are considering this orbit ring. So if xy is x comma y, this vector belongs to this orbit of the vector 1, 0, then xy has to be this. Okay, for some t0 lying between 0 and 2 pi. Okay, and this from the definition of the flow map that we are considering. What is this definition? Let me write it for you here. So theta t comma pq was this. Cosine t is a rotation by angle t, minus sine t, cosine t, pq. Okay, so this was the definition of the flow map. So using this definition, so we take t to be t0 and p to be 1 and q to be 0, and then this becomes cosine t0, okay, and sine t0. Okay, good. So far so good. So this is how the orbit looks like. Right. So it's setting. Now we're setting Tm a sequence of real numbers, which is t0 plus 2 pi m. Okay. So for each m being in the set of natural numbers, we get a real number Tm, which is t0 plus 2 pi m. One immediately observes that Tm goes to infinity as m approaches infinity. Okay, you can immediately see that as m approaches infinity, Tm also goes to infinity. And x comma y is equal to, so if I choose theta Tm 1 comma 0, so you see that way you're gonna have cosine Tm sine Tm, right? And now write cosine. What is Tm? Tm is going to be T0 plus 2 pi m, and this is sine T0 plus 2 pi m. M is any natural number. For any natural number, this is from using the periodicity of this cosine function and the sine function. This can be written down as cosine T0, and this can be written down as sine T0. Okay. And this is precisely x comma y, right? Good. So consequently, xy is nothing but the limiting expression of this theta Tm 1 comma 0 as m approaches infinity, right? And hence one obtains x comma y belongs to the omega limit set of the orbit of 1, 0. Okay. Okay. So we have been able to prove that gamma 1, 0, so the orbit of 1 comma 0, or the orbit of the vector 1, 0, we have chosen xy to be in this set, right? And then we ended up proving that xy also belongs to this set, which proves that the gamma sub vector 1, 0 is a subset of omega limit set of the orbit of the vector 1, 0. Okay, good. This is equation number 14. Now I need some space here. I think this is good enough. Now let PQ be an element of this omega limit set of the orbit of the vector 1, 0. Then there exists a sequence of real numbers from the definition of the omega limit set of an orbit. We know that there exists a sequence of real numbers Tn such that Tm goes to infinity as m goes to infinity, and the limit of this expression as m approaches infinity is equal to p comma q. This is our equation number 15. So this is the this follows from the definition of an omega limit set of an orbit. Okay, but note that since theta Tm 1, 0 is equal to cosine Tm, as we have seen earlier, sine Tm for all m in the set of natural numbers, the norm of this vector is going to be 1. The norm of this vector Tn 1, 0 is going to be 1 for all m in the set of natural numbers. One must have the limit of this guy, the limit of this norm 1, 0, the limit of the norm of this vector as m approaches infinity is going to be the norm of the limit, right? Because norm is a continuous function. The norm of the limit by the fact that norm is a continuous function. Continuous function. Okay. Then by equation 15, this is what we have written down here. Then by equation 15, one obtains the norm of p comma q, the norm of this vector is so let me write, and I think I erase this thing. Okay, so the norm of this vector is going to be equal to 1. Okay, so now from the phase portrait of the underlying dynamical system, which we have seen earlier, that these are concentric circles and the singleton 0, 0. Okay, now from the phase portrait means the depiction of all the orbits in a diagram. Phase portrait of the underlying dynamical system, one sees that p comma q has to be in the orbit of the vector 1, 0, because the orbit of the point 1, 0 is the circle of radius 1 centered at 0, 0. And since p square plus q square is equal to 1, right, one must have PQ belonging to the orbit, this orbit. Consequently, the omega limit set of the orbit of 1, 0 is a subset of the orbit of 1, 0. So this way we prove the reverse inclusion, and hence we have omega limit set of the orbit of 1, 0 to be equal to the orbit of the vector 1, 0. Okay, good. So this is the end of lecture 4. Thank you for attending the 4th lecture of the course of Dynamical Systems.